The American Geophysical Union welcomes you to the Union session, Confounding Major Disasters in 2019 to 2020, with presentations by Suggy Cohen, University of Alabama, Lydia Moraska, Queensland University of Technology, William Lau, University of Maryland, College Park, Bill Fry, GNS Science, Menas Kafatos, Chapman University, Mark Svoboda, University of Nebraska-Lincoln, Vasilios Karastathis, National Observatory of Athens.
My name is Sagi Cohen. I'm from the University of Alabama in Tuscaloosa. I would first like to acknowledge the co-author of this presentation as well as the many other people who contributed to this topic. In this presentation, I want to focus on a tool we developed to augment near real-time remote sensing of floods with water depth and impact assessment. So information about flood inundation is important for many reasons, including to understand the exposure of community, changes in water storage volume, flood hazards, as well as response to floods as a natural disaster. Remote sensing analysis is very useful in this context because it can provide large-scale surveillance on flood inundation, both in near real time and also in historical perspective, but the remote sensing by itself cannot readily use to calculate the depth of the water. Mapping floodwater depth is important because it gives us an assessment of damage and exposure. Right? There's a big difference between a flooding of a few centimeters to a few meters. Hydraulic models can be used to simulate water dynamics and by that provide water depth at great detail. However, flood maps are very expensive in terms of computational time, but also they demand quite a bit of data that is not always available, especially in real time. To address this limitation, we developed what we call the floodwater depth estimation tool, FwDET, which requires little input data, basically just a digital elevation model and a flood extent map. And thanks to that, it actually is very computationally efficient and can be used over large-scale application, but also very quickly in near real time. The first version of this tool was developed a few years ago and was first published in 2018. In that 2018 paper, we outlined the concept behind this tool, and as you'll see, it's a very simple GIS-based approach. Basically, the concept is if you know what is the location of the flood through a flood map, through remote sensing, and you know what is the elevation at the boundary of the flood, for example, over here at 100 meters, this cartoonish cross-section, then because we have knowledge on the elevation at any point within the flood domain, then we can very quickly and efficiently calculate the water depth by subtracting the local floodwater elevation to the local topography. So we developed a script within GIS to automate this process. So all you need to give it is a flood map and a DEM. And I'm not going to go through all the steps, but I would refer you to this 2018 paper in JARA. Version 2 of the tool was trying to address some of the difficulty or challenges in trying to apply such a topography-based tool to coastal regions. The main challenges in coastal regions are that you have very low topographic gradient and therefore you require very high resolution input. The second challenge is the fact that actually the ocean boundary of that flood is open, right? There's no limit to it because we are talking about ocean water that are flooding the coast. And therefore, on the right-hand side in this diagram, we need to account for the fact that we actually don't have any elevation to speak of, and we only need to calculate our flooding based on the most inland boundary of the flood map. So we made some improvement to the tool in order for one, address that open boundary condition, but also to improve the computational efficiency of the tool and therefore make it more feasible to use in very high resolution. The third version, which was just published, is implementing and improving FwDET within Google Earth Engine. The advantage of using Google Earth Engine is the fact that we can streamline the application of FwDET by taking advantage of the resources that are already available within Google Earth Engine, and the ability to scale up that process across large domains because of Google Earth Engine computational power. Google Earth Engine also allows us to develop applications that are more easily shareable and therefore make very nice visualization that end users can use very quickly and easily. FwDET in Google Earth Engine implemented several improvements. One of them was the ability to identify and deal with outliers in the boundary elevation conditioning that we set up as the first step. So we used some smoothing and outlier identification approach to deal with that. We also have the ability to incorporate water bodies layers within Google Earth Engine and therefore take into account permanent water bodies within our calculation. We also incorporate a building footprint layer within Google Earth Engine to allow us to immediately estimate damage by overlaying building footprint on top of the flood map. For more information about the Google Earth Engine implementation, I would refer you to this reference here, again, a paper that was just published in IEEE. So over the different versions of FwDET, we evaluated it over several case studies, including very high resolution flood maps, more coarse and large scale resolution flood maps, even much coarser than that. I'm not going to show you all the validations, and coastal flooding that we estimated. In all cases, we evaluate the tool against hydraulic model. Because we don't have continuous flood water depth maps that we can evaluate against, we need to generate them with a fluid dynamic and hydraulic model. And that allows us to have pseudo ground truth or a more robust estimation of water depth that we can evaluate against. The Google Earth Engine implementation of FwDET was also evaluated in this latest paper, and generally the results of all of these evaluations are really good, both at large scale and at very fine resolution. So the root mean square error that we got was 0.62, so sub-meter average error that we got for that specific case study, and that error is fairly consistent across all the evaluation. Another big advantage, as we said, is that Google Earth Engine has superior computational resources. For example, for this case study, which is 54 square kilometer, it only takes 4 minutes from running until you export the output. We've been using the tool from an early stage to respond to flood disasters across the world. We are members of the Global Flood Partnership, which is a partnership of scientists and practitioners that aim to promote global collaboration towards better flood mapping and flood response. So these are just some examples. There were many more. Almost any global flood partnership activation, we've been involved. And what we do is we take the best flood map that we can get from near real-time remote sensing and add the flood water depth to it. In this example on the left, you see this is from Hurricane Harvey over coastal Texas. And you can see here that we actually overlay address point over flood map, and so we can have a synoptic view of damage or response needs. More recently, after the development of the Google Earth Engine version, as I said, we can use Google Earth Engine to generate very interactive and dynamic web application. And this is one example. This was for the 2020 flood in Michigan due to the 2 dam breaks that just happened earlier this year. And here, this is a static screenshot, but you can use this slider to view the differences in flood map and look at the satellite image of that. And you can query, you can look at the buildings in red that are impacted and zoom in, zoom out, everything you can do with a web application. We also use that tool to actually calculate statistics of how many buildings were impacted in Midland, which was the worst impacted urban location, what severity, meaning how deep the water were around that house, and so on. Now, this was a very large flood, So the size of the flood was over 1,000 square kilometer. And to give you a sense of the efficiency of the Google Earth Engine application, it only took 41 minutes to generate this very large floodwater depth map. As a demonstration of the Google Earth Engine application, we also applied it to the entire state of Alabama using the 100-year flood layer from FEMA. And we also used the Microsoft building footprint to again get a sense of how many and where buildings would be impacted. So we calculate the flood water depth for using this 100-year flood map, and then we overlay that within Google Earth Engine with the building footprint. So now we have a very dynamic understanding of potential number of buildings that are impacted, and we can do that obviously everywhere. And because of Google Earth Engine efficiency, this analysis only took 73 minutes, so just over an hour to do the entire state. So some of the next steps that we're going to take, we are developing a standalone application on WaterServe, which is a new water cyber infrastructure that we are currently developing at the University of Alabama. That standalone application will allow users to interact with the Google Earth Engine application without the need to deal with the code, without having an account. So just interact with the website, and through that, the website itself is going to send everything to Earth Engine and get the results back to the user. We are also working on a new application that will also generate the flood map from remote sensing in near real time using Google Earth Engine, and then apply the water depth estimation. We are working with partners at the Global Flood Partnership and the NASA Earth Science Disaster Program to make it part of the response to flooding disasters. Future research will include the evaluation of this tool with different type of DEMs, different resolution of DEMs, to give some better advice to future users about which DEM they should use in different location. We also hope to validate it more robustly against field data rather than simulated floodwater depth. That is a difficult task because there's not a lot of water depth estimation out there. And we also want to expand the flood impact analysis from going beyond just building footprint and get a sense of the economic or damage and then social impact of floods, both in near real time and historical floods. Finally, these are the three papers that I mentioned. Version 1 and 2 of FwDET are available as ArcGIS and QGIS script tools that are freely available on our GitHub. And the Google Earth Engine code is also freely available on the Harvard Dataverse repository. So these are the links, and I'll be happy to send you those. If you want to shoot me an email, I'll be happy to collaborate on any of this.
Good morning, and thank you for inviting me to give this presentation, Physics of the Virus and Why it Matters. Several aspects of the physics of the virus. Firstly, particle atomization in respiratory activities, instrumental techniques to study the particles, which is physics of them, dynamics of the virus-laden particles in the air, and finally, physics of particle deposition upon inhalation. I'll start with saying a few words about particle atomization in respiratory activities. Atomization in an atomizer is a very simple process, but in human respiratory tract it's far more complicated. Firstly, if we look in the deeper parts of the respiratory tract, here in the bronchial region, fluid blockages may form upon exhalation, and then they burst during the next inhalation, producing particles. Somewhat different process takes place upper in the larynx, and heats particle aerosolation during voicing vocal cord vibrations. And finally, saliva in the mouth is aerosolized during interaction with tongue, teeth, and so on during speech articulation. This is not the end of the complexity, because after formation, somewhere in the respiratory tract, this particle undergo further processes before they are respired. And in particular, traveling upwards, they are deposited, and this changes the initial size distribution. The complexity continues. There was a recent science paper explaining potential surface deformation and what it could do to particles like this. So, as I said, this is a mind-boggling physics of this process. We don't know that much about this, but we know quite a lot what is after the particles are expired. However, here is the question how we measure this. I'll give an example of this and a second way it can be done. This is how it was done in our study, where a person was sitting in a flow tunnel and particles of various sizes were measured by a range of different instruments to then characterize the whole size distribution. A different instrumental technique was used in this study by Zayas and colleagues. In this case, the researchers employed the laser diffraction system, and they were able to investigate much broader size distribution, extending to lower submicrometer range particles as well as larger particles. There are many ways particles can be investigated and the physics which is used for this. The point is not that much that it is measured, something always be detected, but how it is quantified and what methods are used to quantitatively characterize the size distributions and concentrations. So what comes out in terms of our understanding is this. This is an example of size distribution measured in the first experimental design. And as you can see, the vast majority here of the particles are below 10 micrometers, and the concentrations are much higher with the decrease in size of the particles. According to the study of Zayas, the second design, there are also particles and quite large quantities in the range below 1 micrometer where the distribution extends. So these are all particles. Now the question, where is the virus in this particle? The first point is that in relation to this virus, SARS-CoV-2, a naked virus is of the order of 0.12 micrometer, but size of the virus-laden particles is bigger than this. And this is because particles are aerosolized with other constituents, water, mucus, salts, and so on, which means these particles are always bigger. How much bigger are the particles containing the virus? Recent studies by Santarpia and colleagues and our study in China show that the majority of particles containing the virus are smaller than 1 micrometer. So this is the conclusion: majority within the mid-submicrometer range and larger of the particles containing the virus. So what happens to the particles of this size in the air, the dynamics of virus-laden particles in the air? As schematically presented in these diagrams, these particles which are bigger are taken by gravity and removed from the air very quickly and in close proximity to the infected person. However, smaller particles stay in the air and undergo various other processes. Again, schematically presented in this diagram. Here the particles in the upper part, the particles filled up the whole room with more or less uniform distribution, with ventilation small. However, on the lower panel, the particles follow the flow of the air towards the window or the mechanical ventilation vent. So basically, the processes or the physics here is gravitational deposition of larger particles at the time it takes, flow dynamics of smaller particles, and removal by ventilation of the small particles in the air, and other processes as well, but normally ventilation is by far the most important process. So finally, what happens with the particles when they are inhaled by susceptible people who share the room with infected people? Particle deposition in the respiratory tract. This diagram presents the deposition as a fraction as a function of particle diameter for different parts of the respiratory tract. In the deeper part of the respiratory tract, deposition is mainly by diffusional processes. However, in the upper parts, larger particles is impaction and interception. Our size distribution of interest is marked here below 10 micrometers to meet a submicrometer range. So larger of these particles will be deposited in the nasal part of the respiratory tract, but only the smaller can travel deeper and get deposited there by maybe by diffusion, but not all. So in summary, physics plays a key role in generation of the virus-laden particles from human respiratory activities, detection and measurements of these particles, then plays a role in what happens to this particle in the air. It is transport and removal dynamics, and finally deposition of the particles in the respiratory tract upon inhalation. Therefore, physics of the transmission of respiratory infections matters and is important to understand. And I'm stressing it's not just of this virus, but of any viruses, respiratory viruses, which affect us quite common. Thank you very much for your attention, and goodbye.
Okay, I am going to talk about regional climate feedback exacerbating wildfires in the Western United States. This is a joint work with Lei Zhang and Wade W. Tao, and also Zhang Lane from University of Maryland, and also Kim Kim from NASA Goddard. Yeah, this work is actually done and the paper published about 2 weeks before the wildfire in California. So talk about bad timing. I think if that had been delayed like 2-3 weeks, this paper would get a lot more attention. But anyway, I'm going to talk about that, and so about the so much is about the people talk about the wildfire now in the Western U.S., but this work is really on the trends of the wildfire in the Western U.S. region, and of course 2020 is not included in this analysis. But anyway, you will see that a lot of the things we talked about is highly relevant to what we're seeing now in the Western US region. So this is a list of the key drivers for the wildfire in the US: drier vegetation, increased flammability, increased vapor pressure deficit, something which atmospheric scientists, we related to the relative humidity change, increased lightning, wildfire, heat and pyrocumulus exacerbating wildfire, other factors including bark beetle infestation, forest management, and I will be focusing on regional climate feedback and specifically why the Western US region, okay? So this is actually some work that people have done, published very recently in 2020. Basically, there is a long-term trend in the warming in the Western US region, and the fire weather index, which is using meteorological data, temperature, relative humidity, and other factors, and wind, that give you that this fire weather index has been increasing since 1980 all the way to 2019. And there is also no question that from the CIMI-5 model, that if you look at present day and 21st century projection of 1 degree warming and 5 degree warming, you clearly see that there has been increasing fire potential in the Western US. There's no question, and all the CIMI models seem to agree on that. So there's really no question that it is. But the real question that I have in doing this is, why the Western US in particular? Are there any regions similar to the Western US? So that's where the work starts. So basically, before I talk about that, I bring in another previous work which talk about the change of the ITZZ convection in the intertropical convergence zone in the tropics. In most studies, when you are interested in Western US, you will be simply interested in precipitation and dryness over the Western US. Why do you worry about precipitation over the ocean? Well, it turns out we find out there's a strong connection. So here is another global warming kind of consensus result, showing that some of the work done by ourselves and others, showing that under 2 times or 4 times CO2, there is this very a strong feedback or signal in the ITCZ structure. There is a narrowing intensification of the ITCZ, more high clouds in the deep tropics, and a deeper headly circulation, increased subsidence and low level, increased tropospheric warming and near surface drying. These are the two important factors that is affecting the subtropical region, and you can actually see it is simply the fact that this one shows us this model result, indicating that under the global warming, you would have a warmer atmosphere, but if you look at the relative humidity field, it is actually a very strong reduction. You are seeing drying over the upper troposphere, the middle troposphere, and also in the subtropical region, 30 to 60 north, where the western US situated, is actually a very strong dry arm relative to humidity coming down. So we call it the deep tropical squeeze. So you got rising motion here, and then you get the convergence towards the equator, but then you got drying all over the deep, the troposphere and also the subtropical region. So that is where as the starting point. So you can see that drying actually reflected in the precipitation field. If you look at the seasonal variations, here's the ITCZ. So from December, January, February, and March, April, May, and June, July, August, the northern ITCZ is strongest. And the region of the subsidence over the western US is actually also strongest. You can see this blue area is a strong drying region. So seasonally, you have the June, July, August with the strongest ITCZ and the strongest drying going on that affect the western US region. And so our approach for this study actually use what we call the balance of evidence approach. We don't use a single data set, but we use a diverse, independent data set for 30 years. This is a relatively short period from a climate warming point of view, but we use this balance of evidence approach. That means all this set of observations are kind of independent to each other. The most important one, obviously, is a fire burn area. And then we have the land surface relative humidity, cloud amount, surface radiation, the drought index, precipitation, and meteorology from 5 reanalysis data. There are more than 10 or 15 different data sets that you use in order to come up with our answer. Well, basically, we look at the North American region and try to find a region from the burning index for the last 30 years, which shows a significant trend. So we first of all, we noticed that the yellow indicating positive trend, that means increasing large wildfire. The blue areas indicate the less. So you can see the significant area are the positive area. That means there is increase. So we find increase in the western US, in North, in Canada, Western Canada, and also in Alaska. But if we look at the time series, we can see the western US, this trend is very robust with interannual variability. Over Alaska, this trend, if you remove these 2 years, you don't really see too much of a trend. It is very large wildfire. In the West Canada, it's the same situation. You don't get a very strong warming. And then if you look at the correlation between all the relative humidity, the cloud amount, and the shortwave downward radiation, and the PDSI, which measure the dryness, you can see it's a high correlation of all this over the western US. And if you do the same for Alaska and other regions, you just don't see the high correlation. So the western US has experienced a drying and also reduction in cloudiness and the shortwave increase in shortwave downward radiation and increasing dryness. Okay, so that's the last 30 years. So if you look back at this picture, the first picture I saw, if you use the reanalysis, you can see that this is a global warming signal. The drying of the subtropics, this blue area, can be seen in this region, and there's warming here. So all the 5 reanalysis shows that in the last 30 years, we can detect this global warming signal. This global warming signal is associated with an enhancement of the subtropical high. You can see the anomalous circulation, and then you see this high circulation, which is increased offshore flow from the western US region out to this region. So this is a very indicative of the increase that people talked about, the increased offshore and drying flow. And then if you look at the subsidence, this dotted region means the increased subsidence, and the blue area means the reduced precipitation. in this area. So this whole area, not just the Western US, the entire North Pacific is actually getting drier in this situation. So if you look at the Western US region, you can see this curve is the relative humidity. You can see it's drying in the upper troposphere, and also there's a peak in the lower troposphere, which is then related to the downward wind. And then you can see the warming, which is this red curve here, and extend over the entire troposphere. And also the downward motion, which is represented by blue curve here, is representing very strong downward motion through the entire troposphere. So this is much more than just a surface phenomenon, but the entire whole troposphere. So in the Western US, you see this very strong feedback, which is warming and drying by adiabatic compression of the sinking air. If you look at the Alaskan region, you don't actually see this. You can see there's a reduction, but you don't see the robust false positive feedback. In the same way with Western Canada region, you don't see that same kind of strong signal. So you don't see this regional feedback in there. So basically, I can the result is consistent with this familiar picture, which is from drawn from NOAA. Basically, what we see in the long-term term is this increased anticyclonic high offshore flow, and then we have the downward flows that's warming and drying and warming and drying. And this region is very much specific to the Western US as compared to Alaska or Canada. You don't have the topographic forcing. So that's our main result. So I conclude with this last slide, basically saying that if increase, we provide a missing link, which is this box here, confirming the idea that increased greenhouse gas emission with intensification of the IDCC actually lead to increased vapor pressure deficit. And this positive feedback is what we are saying. And then of course, the big question is whether this wildfire itself would actually provide feedback and enhancing the global warming signal. And the other factor which I have not looked at is sea surface temperature impact on that. So I basically conclude that our results are very much consistent with what we are seeing in the Western US at this moment.
Good morning or good afternoon, everyone. Today I'm going to tell you about some thinking we have around how to ensure that our exposed coastal communities that suffer tsunami risk should respond or give a framework for them to respond in the presence of competing hazards. This was most recently brought to our attention with the COVID-19 pandemic, when questions around evacuation and the breaking of self-isolation might create competing priorities for public safety. I'm giving this talk and I'm from Te Puʻao, which is the National Survey of New Zealand. My co-author, Laura Kong, is from the International Tsunami Information Center, which is part of the IOC UNESCO and closely affiliated with the Pacific Tsunami Warning System. Anything I say today, if I make mistakes or say things you don't agree with, please blame me and not my co-author, Laura. I'm going to start with the conclusion, so if you do tune out, at least I've left you with this thought. And that's that when we make a decision for life safety in government or any sort of response community, we have to weigh two competing interests, one of precaution and one of proportionality. Precaution being an underlying idea that we do whatever is necessary for life safety, and proportionality being a legal and a government concept in which we weigh off the imposition of a decision versus the benefits of the decision. And many times those are competing interests. And at the end of the day, the best way we can define a very good balance between these two ideas of precaution and proportionality is with peacetime relationships. So we need to have open communication between scientists and end users, emergency responders, central government, regional governments, prior to the event actually happening, to have a framework in place with which to make the most appropriate decision. When we talk about precaution and natural hazard response, in many cases, this is an implicit concept. And in some cases, it's an explicit concept. Coming from a government-owned survey in New Zealand, I'll give you an example from our our statutory framework, and that's from our Civil Defense and Emergency Management Act, which says all persons exercising functions in relation to the development and implementation of civil defense emergency management plans under this act may be cautious in managing risks, even if there is scientific and technical uncertainty about those risks. I've highlighted in red scientific and technical uncertainty because that's the situation in which we are inevitably finding ourselves in when there's a big earthquake and subsequent tsunami. So in this situation, we have some sort of statistical models or purely deterministic models that we understand there are a range of uncertainties, aleatory uncertainty or aleatory variability and epistemic uncertainty, which affects our forecast. So there's uncertainty in the information we're using to underpin these decisions. And the response community has the explicit privilege of using a precautionary response, of taking a large-scale action to encompass the uncertainties of our scientific knowledge. Then there's a competing interest in proportionality. So proportionality is a doctrinal tool that somehow tries to balance the benefit of taking an action with the imposition of taking that action. So it says that the action you take needs to be proportional. It needs to be commensurate with the benefit that you're receiving from it. And in many times, it's not so clear cut. If you take a decision to make everyone safe, you might be creating a situation in which one person is in position more than the other. If we take an example from tsunamis, which is what I've shown below, this is a simulation of the 1960 M9.5 tsunami or earthquake and resulting tsunami in the right-hand side, with the colors showing you the open ocean amplitude of the waves and this asymmetric radiation pattern that extended from South America up through the Central Pacific. And here's New Zealand down here with the green box around it. So this is an example from New Zealand in which you see time since the earthquake on the x-axis and amplitude of at a random spot, or not a random spot, a spot next to the coast by a populated urban area in New Zealand. So what you see is after about 12 hours after the earthquake, you start getting waves arriving, and I've put in a yellow bar here, which corresponds to our land threat or land evacuation level. So if we get waves on land above this yellow bar, we think that's dangerous to people and we need to evacuate the coast. But what you can see is the tsunami wave train. So this time domain signal goes above that yellow line time and time again. So from 12 hours after the earthquake up to really 29 hours here when the simulation stops, it's still touching this bar. So I'm using this to highlight the difference between precaution and proportionality. A precautionary approach would say, well, we know at least for the first 30 hours or so that we're getting waves above this 1 meter threshold, and this, who knows how long this is going to continue. This might continue for another 24 hours. So let's just say get everyone away from the coast in all locations for the next 2 days, for example. But a proportional response might say, well, these people, they need to somehow return to their houses, to their coastal communities. And it makes a difference if they return at the 30-hour period or if they return at the 48-hour period. So where should we make that decision and allow people as response managers, allow people to return to those communities? So this is what that looks like. And conceptually, this is just a cartoon I'm trying to show you. On the left-hand side is the precautionary approach. Say if you have a tsunami evacuation without a pandemic, then you can have this large scale of response. You can have widespread evacuation, and that's perhaps based on a concept that we call maximum credible scenario or maximum credible event, and I'll discuss that in a subsequent slide. On the other side is a proportional response in which you see a smaller scale of response, so less evacuation, perhaps based on a most likely scenario rather than the maximum credible scenario. Of course, in practice, there are diagonal lines connecting these two, and the ideal solution for decision makers is probably somewhere in between. So when we talk about maximum credible event or maximum credible scenario versus most likely event, we might imagine some sort of population density of models. So in the case of A up here, we're looking at numbers of cases of COVID fatalities increasing to the right-hand side. On the y-axis, we're looking at number of sunny days during during the response, and I chose sunny days just arbitrarily. You might imagine there's some sort of link between a sunny day and the number of cases that are transmitted. Say, for example, on sunny days, people have barbecues, they get together, they go outside, or the other way around, sunny days, people feel more empowered to go out in nature and remove themselves from other people. I don't know how that works, but just imagine, for example, that there's a population distribution of COVID fatalities that's dependent on one parameter. If you take a cross section through that distribution, say like in B, you get some sort of distribution like this, and the maximum credible event, we might pick somewhere over in this area here. If we just draw a vertical line right in here, but the most likely event's going to be some sort of population distribution right around the center. So this maximum credible event and the width of the most likely event are arbitrary and need to be chosen with a clear understanding of all of the competing interests. C is just showing that with a reduction in epistemic uncertainty or an increase in epistemic uncertainty, we might flatten this curve, or we might make it more narrowly defined, meaning that that population is narrower and the decisions are easier to make. So when we have something like that, how do we actually go to the process of making a decision on evacuation based on it? The plots on the right, which were provided by a colleague, Nick Horspool, are a way in risk space. So risk is taking the hazard through to some sort of impact. So quantifying the hazard and the exposure and how that's going to affect humans or the built environment. So just look at the top plot here, which is a tsunami death rate. So this is the percentage of people exposed to water depth. So this is an inundation depth of the tsunami. And if you might imagine, you plot a best fit line through that, you can predict with any given water depth what percentage of the exposed population might suffer death if there's no evacuation. So you can use a fatality function like this to bridge the gap between trying to quantify the optimum place in this proportionality of response to make a judgment call on evacuation. Again, the example of 1960 Chile tsunami, if you do the math and you simulate the amount of inundation, say in Napier, it's a New Zealand city on the East Coast, right in the yellow box, and you use this fatality function, you might imagine that this earthquake would have generated 40 fatalities with no evacuation at all, and today's current population density. So if you stop and take a step back and you look at that in terms of the relative impact of that versus the relative impact of an evacuation and its effects on COVID transmission or any other sort of natural hazard or man-made hazard like that, then you can take the same sorts of models but made in the medical space with different R0s. R0 is an infectivity or a communication rate of COVID, for example. And you might come up with a number like a number of 40 for this whole population center if you have a really precautious approach to evacuation. So it's weighing off the balances of evacuating or not evacuating, and that cautious, that number of 40 is with a very high R0. It's probably a lot less than that. So this is probably overestimating a lot the impact of the evacuation in this scenario. But this sort of analysis allows you to say, well, yes, we need to evacuate. We've got to get people away from the coast because the impending tsunami is their most present danger. That's always the most present danger, but it might allow decision makers to scale back somehow where they apply that precautionary approach and have a smaller area of evacuation, for example. So to conclude, we're always balancing proportionality and precaution. And to do that, we need to understand the relative ranges of forecasts, of models, the relative ranges of the scientific advice. In order to compare those, we have to take that through to a risk calculation, and we have to communicate those things to the decision makers in peacetime prior to the onset of the disaster. Thank you.
Good morning, everybody. My name is Minas Cafados, and I'm reaching you for this presentation with my co-authors, Shanyu Jia, Sung-Hee Kim, and Sung Yam. Paul Doherty. The presentation is crowdsourced data assisting disaster relief practices in the era of social sensing. So in terms of the abstract, we have an effective way to monitor human activities, which are crowdsourced data collected during major disasters. And that they have received quite a bit of attention in development and response to these disasters. So we investigate patterns of population displacement during megafires, COVID-19 pandemics, of course, and other disasters using Facebook disaster maps. We demonstrate an operational application to retrieve these spatial and temporary displacements in a timely fashion using the emerging hotspots, and to furthermore pinpoint challenges in application of crowdsourced data, which include the need to conduct a comprehensive evaluation, the representatives of data, necessity to develop recommendations for policymakers on the most appropriate usage of such crowdsourced data to be used during an emergency. And we also point to the possibility of using remote sensing data towards fusion method and to reduce bias without violating users' digital privacy. Last but not least, we show the importance of better understanding, if you like, of needs from the front line to bridge the gap between scientific research and the deliverables needed in actual decision maker. So the crowdsourced data in emergency research and applications have to do with providing timely and spatially accurate representation of human activities. Applications have soared during the COVID-19 pandemic, of course. However, privacy concerns remain, and we need more data openness and method transparency. So we also have a need for more analysis-ready data sets. There are some challenges, such as high technical bar to utilize geotagged social media data, and to have analysis-ready crowdsourced data, which allow users to focus on product and solution development. Some examples of crowdsourced data analysis are food traffic points of interest, POI, and app usage at time T and location X and Y. I would like to show here a quick video, but the question is, what can be done with analysis-ready crowdsourced data? So we have to monitor evacuation process before, during, and after disaster, optimize resource allocation for emergency response, and couple with other metrics for in-depth analysis. So playing this video for you, you can see how the patterns are changing, and from the red to the blue or purple. And so we monitor evacuation before, during, and after, as I said, optimize resource allocation for emergency response, and coupled with other metrics for in-depth analysis. So, okay, moving on to our next slide. We have here 3 panels. You see, on the left panel is a data cube that basically illustrates the population Z-score based on Facebook disaster maps. So the population is aggregated into 1 kilometer grids, which are provided every 8 hours during the fire disaster. So basically you have normalized difference in Facebook users detected between crisis time and normal time. On the center panel, we see that we can identify data breakpoints in population time series and track community response. On the right side, we identified hotspot analysis to detect aggregations of populations, and of course, track movements of population. So here we have examples of the Worsley fire. On the left panel, upper left side, you see the actual locations. On the right panel, on the top, it's the actual quick return evacuation. Order lifted shortly after pause, and then the population returns, and you see the different locations, how they faster return. On the lower panel is when the return is slower, and in the last panel on the right is in fact, when there's no change, no evacuation. So we Facebook disaster maps population change separated into regions based on the time series patterns. Here we show two particular fires, the Woolsey fire on the left side and the Mendocino complex fire on the right panel. And so here you have, if you like, in the case of the Woolsey fire, the less people use FEMA shelters. FEMA shelters shown with the cross. And on the right panel, you have more people use FEMA shelters as the fire occurred in remote areas. The red dots are more people, and the blue dots are fewer people. So you see how the patterns are different in the two cases. Now let's turn our attention into challenges. So lack of communication between first responders, emergency response, to developers who are specialized in using GIS, and then importers or data producers into the tools. We need to have acting proactively, not responsibly. Of course, that's always difficult in a real situation. And use crowdsourced technologies to help data scarce countries, regions, because there are many regions, in fact, that cannot be reached very easily, such as mountain areas, etc. So there are, in fact, if you like, miscommunication between the players in the game, the responders, the tool developers, and then the usage of the data. And if you have a good situation, you can have a feedback, as shown on the left side. But if not, then you need to be preparing the data in the right way, as shown on the right side with the arrow pointing. So two developers lack understanding of actual needs at sea. That's one of the issues. Two developers are also often in a responsive mode rather than proactive mode, as we said before. And sometimes, in fact, we have to reinvent the wheel under similar circumstances, which, of course, is something that needs to be avoided. So we need to have a way to act proactively and be ready. Data need to be pre-identified. Access needs to renegotiate across different stakeholders. That's not always easy because you have to coordinate things, evaluate the data quality, strength, weaknesses, representativeness. Are the data really representing this real situation? And develop methods to address actual needs. And finally, of course, scalability. It needs to be considered so we can address specific situations. We have, as I indicated before, data-rich countries, regions, areas, so to speak, and data-scarce countries, regions. So we have to evaluate the quality of the data, develop experience of data usage, and inherit the legacy from traditional methods to this new way. For data-scarce regions, use crowdsourced technologies as a new way of data collection and fill in the gap as needed. Make, in fact, all of this more internationally usable, which will, of course, gain experience from other people using it. I want to close by just showing you a particular situation on the Beirut explosion. On the three panels show you the Z-score, more people than usual is in yellow, so to speak, lighter color, and less people than usual, deep dark purple. You can see in sort of like a time series or time sequence, how the situation returned back to normal. And when, in fact, the people gradually return after days of the explosion, the purple grids grew smaller and smaller. I would like to thank you all for your attention. I would like to thank my co-workers, collaborators, and have a good day. Thank you so much.
Hello, my name is Mark Sabota, and I'm the director of the National Drought Mitigation Center at the University of Nebraska-Lincoln. Thanks for joining me today. I want to speak to you a little bit about an emerging topic in our field called flash droughts, and the idea of can we change the drought early warning paradigm. What is flash drought? Well, just like all other droughts, there is no one definition. There's various types of droughts, and it takes various types of indicators to monitor and or define them. I think the same holds true for flash drought depending on your location and application. In general, though, we tend to, if I could borrow from the American Meteorological Society's meteorology glossary, we define it as an unusually rapid onset drought event characterized by a multi-week period of accelerated intensification that culminates in impacts. And I think that's an important distinction, because if you don't have impacts, some would argue, are you in a drought? So how do we get here? If we take a little deeper dive and go back through time and history of how this term has evolved, first coined back in 2002 in the context of the U.S. Drought Monitor, and at least being aware of the need to take into account these rapid onset droughts. That was sort of in an operational context. Defining it didn't come along until later, particularly after the iconic 2012 flash drought. A couple seminal papers between 2014 and 18 and 20 came about. I'm just showing a few here, certainly not an exhaustive list. For that, I think you'd want to look at the last bullet. Soon to be out there is going to be the results of the extensive literature review that the National Integrated Drought Information System conducted, and also out of the results of the workshop that was conducted just a week ago, actually. But prior to that, efforts were made to bring in experts from around the world to the Aspen Global Change Institute to look at subseasonal to seasonal forecasting with a main focus on flash drought. This resulted in the Nature paper to the right you see here about flash droughts present a new challenge for subseasonal to seasonal prediction. So that's out there for you to take a look at as well. So there's been a lot of mushrooming of the interest in topics here over the last 5 years in particular. So we think of these as more intra-seasonal. I think the traditional mindset is drought's a very sneaky, slow onset disaster. And what we're trying to show here is that depending on the time of year, depending on the region, these droughts can intensify quickly and cause major impacts in just a few weeks, on the order of 4 to 8 weeks, 10 weeks, somewhere in that neighborhood, and not 4 to 8 or 10 months necessarily. So it's not the only type, again, not the only type of drought, but I think the awareness of this rapid onset drought and the impacts that can come certainly could linger weeks or months and become an agricultural drought or a hydrological drought, more of the traditional definitions you're probably familiar with, that affect so many sectors. So I think there's a need for the awareness of this new kid on the block. And Dr. Kelly Redmond always used to say to me and to anyone else that would listen, if there aren't any impacts, are you in a drought? So that concept of the impact component piece, I think, is pretty critical if we want to think of this in the context of drought. And of course, I touched on this just a little earlier. Context matters. So timing is our parallel to location in the real estate business. That timing by region, by season is critical on the sort of impacts you can expect to have happen. Some of the origin story, if you will, if we can do a little Marvel comic analog here, is to look at when I was doing the Drought Monitor and authoring that product, when we first created it back in the late 90s and the early 2000s. This particular drought is where I remember using the term in the media. And it was to catch people's attention. That was on purpose, to get them to think about drought in a different way and to raise the awareness of drought and the need to see it as something that can evolve quickly. And this example of really late season, hot, dry, windy weather that came across the southern plains in 2000 did the trick. And so you can see I've circled in red here on the table how we basically went from severe drought of less than 2% to over 80% in just 3 months' time. So you can see rapid deterioration and rapid impacts come on very quickly. So this was sort of the first time I started thinking about it, and that's what led to the inclusion in the 2002 BAMS article on the U.S. Drought Monitor. Now, the more iconic cases are 2012 and 2017. 2012, which ended up blossoming into a huge amount of drought across the U.S., many places, well, countrywide, as much as you would have seen almost at the apex of the Dust Bowl peak years as well, for at least just spatial coverage of any sort of drought. But for this region in particular, in the north central, Midwest, central northern plains, we could see 4 to 5 class degradation in 3 months, and actually even quicker than 3 months if I were to include some other maps, between early May and late July, where things and conditions deteriorated rapidly and impacts became rampant. All sorts of issues that were born out of the 2012 drought, but then further spurred, I believe, research into new tools to help us track it better and enhance the drought monitor going forward. In 2017, our response time was much better, not perfect, but certainly much better in the high plains or northern plains. But we still saw this flash drought occur 3 to 4 to 5 class degradation in a matter of 6 to 8 weeks in that drought of 2017. So is this a climate change signal? It's definitely influenced by temperatures, different cases, different antecedent conditions, just again, timing, location, region, and season. So much more work to do in this area, but pretty exciting to know that we have some new tools at our disposal. These tools I'm speaking about are not only using our existing in situ networks, but also augmenting those, especially in data poor areas, with new remotely sensed products. And I've just included a few down here at the bottom of the screen, with the goal of capturing more of the hydrologic cycle. As you can see here, I've circled those: soil moisture, vegetation stress, evapotranspiration, and rainfall, with the idea that these are uniform, gridded coverage sort of products available countrywide, in some cases continental-wide, or even globally on a pretty good operational, near real-time basis. And we think these are already showing their mettle by helping us better track things like flash drought and the effects on ecological systems. As I mentioned earlier, this has been a way to integrate them into the U.S. Drought Monitor, initially vetting them, tapping into an expert network of over 400 experts on the ground that ground truth and provide a sanity check to the U.S. Drought Monitor every week. We tapped into that community to evaluate those products I showed on the prior slide. And once we saw and felt comfortable and trusted them, began to integrate and ingest them into the U.S. Drought Monitor to help our spatial and temporal resolution and accuracy. So our response to the 2017 drought was on the order of a couple weeks and not a couple months, especially for those droughts that aren't forecasted, of which neither were forecasted. So this has really ramped up our ability to capture these rapidly increasing flash droughts by bringing them into the fold. And again, we just didn't have that capacity in 2012, or I think there would have been a better response. The forecasting element is still very difficult, but improving these blue circles here on the diagram on the bottom left of what can be ingested into the drought monitor, we have a lot of new products in each of those areas that are coming into play with machine learning and GIS to make the drought monitor more accurately reflect these droughts. Some of the challenges and or opportunities, if you want to look at it as a glass half full, drought early warning is definitely a combination of monitoring and forecasting, and not just forecasting. And we know it has to be, because we know we have a long ways to go on increasing the accuracy of our sub-seasonal to seasonal forecast. The other inherent challenge is that droughts are a days to decades spectrum. Very potentially large spatial footprints over large areas, and potentially large temporal footprints over months, years, or in the case of megadroughts, even decades. So the challenge is there. New products are starting to be rolled out and evaluated. CPC, or the Climate Prediction Center, is looking at a new flash drought forecast capacity. I'd say one of the other major challenges, however, is as a lot of these new products are stood up, oftentimes it's very difficult to keep them up operationally. So that investment of the shiny new car up front needs to be followed by good operational maintenance going forward to keep those products in play and not have them fall away after 3 to 5 years as a new tool comes online, because then we lose all that history and institutional memory of those products. The other key part here is that, just like I mentioned with drought, there isn't one single definition, so it's very difficult to have a single driver that's going to provide the complete picture of what is flash drought. And we know that, and many efforts are underway to look at the best ways to take away from the strengths of the various individual parameters or drivers and hopefully mask the weaknesses to make a better end game product, whether that's a blended product, composite indicator, or if it's the drought monitor, or whatever the case may be. And it's my hope that we can begin to change the paradigm, and that flash drought can be the torchbearer for better drought early warning, in order to have policymakers who generally have a short time horizon. Maybe they're only going to be in that position for a couple years. And unless you're in a multi-year drought or a multi-seasonal drought, it's probably not going to capture their attention. Understanding that droughts, like all the other hazards, can be very rapid onset, however, may change that mindset. Because at the end of the day, we just can't have apathy as an excuse for having drought sneak up on us. And having heard that repeated the last 25 years, I think we can do better. A final thought or two here. To me, dealing with flash drought isn't just about changing our tool set, but rather our mindset, especially in regards to planning and decision making. Getting away from the reactive, slow onset mentality and turning our attention more towards quote unquote rapid onset droughts in a proactive way is the way to go. And we can't let the idea that droughts are only slow onset hazards become the only doctrine we follow. I would say it's both. As I mentioned earlier, I believe this may have a better appeal to planners and decision makers, and it's a way to get drought in through that open window at that time, and it's an opportunity to get it on their radar as we try to advocate integration into various planning processes, early warning systems, and into practice and policy when all is said and done. And with that, I'll wrap it up. I thank you for your attention, and if you do have follow-up questions, you can contact me at my email listed here on the screen. Thank you again.
I'm Vasilis Kanastatis from the National Observatory of Athens, and I'll present the results of the continuous radon monitoring in the region of Eastern Gulf of Corinth from 2017 up to now. Although perhaps the precursory phenomena have been proposed, the variations in the noble radioactive gas radon is what has undoubtedly been the most discussed in the past, with extensive literature and wealth of data. Despite the fact that the first evidence came quite early and the research followed was intensive, this pre-earthquake process has not yet exploited as an earthquake forecasting tool. The strong effect of exogenous atmospheric factors, non-systematic measurements, false alarms, and the absence of a reliable model justifying the radon anomalies blurred the picture of the prospects of the method and reduced its initial vigor. Monitoring of all atmospheric parameters and the long-term correlation with the soil radon concentration is actually required. In literature, there are plenty of publications that claim to describe some connection between variations in radon concentration and upcoming earthquake events, but in fact, such an association has been well documented only in limited cases. Experimental research has shown a particularly important direct dependence of radon changes on exogenous factors such as variations of pressure, wind, and temperature. The problem of assessing an anomaly and attributing it to an earthquake becomes even more difficult if we take into consideration the fact that the choice of the occurrence time of the precursor phenomenon is quite arbitrary, without any specific rule. If in simple terms there is an anomaly in the radon concentration before weeks or just a few hours before the earthquake, scientists could possibly interpret it as a precursor of this event. In order to record pre-earthquake anomalies in radon concentration before strong earthquakes, we installed soil radon concentration monitoring stations at high seismicity areas such as the Hellenic Arc in western Greece and also the eastern part of Gulf of Corinth. The installation of the stations began in May 2016, and in all sites, real-time monitoring was established. Today, the network has 7 stations, which are installed in the position shown in the map. The radon network was mainly based on sodium iodine scintillation detectors for gamma spectrometry. The detectors were positioned at 1.5 to 2 meters depth in a shallow cased auger hole. The type of this scintillation detector is of high sensitivity without requiring cooling to liquid interchange temperature. A full spectrum analysis processing is applied to the data, provide us with a very good energy resolution. At all locations, there was a good coverage by meteorological stations with accurate monitoring of all parameters that could affect the radon concentration measurement. 2 gamma-ray radon stations were installed in the region of the eastern Gulf of Corinth. This area is of high seismic potential since a series of 3 major earthquakes of magnitude 6.7, 6.4, and 6.3 occurred in 1981. The region has major faults and has not been very active in recent years. Also, at the periphery of this region, significant earthquakes have occurred in the past. The Gulf of Corinth, one of Earth's most active continental rift systems, is a high seismic hazard area with many catastrophic earthquakes in its history. However, its seismicity rate is not as high compared to other active tectonic systems, such as the Hellenic Arc region. The long quiescent periods between the major seismic events essentially help to have a safe correlation of the possible pre-earthquake radon variation with the seismic events. The main tectonic structures of the Gulf work under an extensional field and consist of regular listric faults with an approximately east-west direction and a slope to the inner part of the Gulf. In the eastern Gulf of Corinth, there are also important active tectonic structures with a northeast-southwest direction, which are associated with strong earthquakes such as the ones of 1981. Nixon et al. In 2016 stressed that along the southern margin of the Gulf of Corinth basin, the North Tipping, North Kyato, and Perahora faults form a dextral and echelon fault array with the East Xylocaster fault, which is probably linked at depth. The extension Lutraki has been installed since October 2017 in a shallow 2-meter borehole at a site close to thermal baths water supply at a high proximity to hot springs. The location of the station is on the hanging wall of the fault that facilitates the hydrothermal flow of the thermal springs. The fault has an east-west direction but extends into the sea with a northwest-southeast direction. Positions near hot springs in the literature appear as favorable for radon measurements, having been considered that better facilitate the transport of radon from long distances. Atmospheric influence of the data has been eliminated due to the high underground thermal gradient in Lutraki station. However, the effect of the long-period tides to the radon exhalation is still noticeable. The wind is the only factor that can influence the data. The strong winds can reduce the level of the radon concentration. As we can see in the spectrum diagram below, the radon showed by black line doesn't follow the diurnal variation of the temperature and the semi-diurnal one of the pressure. A macroscopic view of the data of Psatha station shows that there is a stronger relation between temperature and the measured radon accumulation in the seasonal variation. The data of the station can be interpreted after thorough inspection of the atmospheric data. The overall picture of seismicity during the period of radon monitoring in the eastern Gulf of Corinth shows that there was probably an activation of the previously mentioned fault array. In addition, the Loutraki fault and its offshore extension practically oscillate this structure, which is effectively connected with the main tectonic structure of the Gulf. On December 31, 2017, an earthquake of a moderate MW 4.9 magnitude occurred at the northern margin of the Gulf of Corinth, just opposite to the Perahora Peninsula. The earthquake caused concern among the local population because it occurred at a distance of only about 10 kilometers west of the epicenter of the first devastating and lethal earthquake of 1981. The focal mechanism of the 2017 earthquake, as calculated by Harvard CMT, shows a seismic source with very similar characteristics to those of the earthquake of February 24, 1981. Both the proximity of the epicenters and the similarity of the focal mechanism support the assumption that the 2017 earthquake was originated from the faults on the south margin of the Gulf and probably the fault zone that was activated in 1981. Our observations are compatible with a dilatancy model that proposes an inelastic volumetric increase of rocks prior to failure. Before earthquakes, there is an accumulation of tectonic strain that produces a slow, steady increase of effective stress. As we can see in the radon diagram on the right, during the period before the major events, a steady and slow increase of radon can be noticed. That is possibly due to the increase of cracks in porosity and/or an increase in the flow rate of pore water. However, just before strong events, there is a sudden drop of radon level. The nature of these anomalies resemble anomalies in stress, as observed in the example below. At Loutraki station, we observed that the drop of the radon level was followed by a significant increase in seismicity, which lasts to this day in the area. In the seismicity time map, we can see the latest events with red color. Thorium, shown with green line, and also potassium were both very stable during the radon monitoring, showing the consistency of the measurements. The gaps in the data were mainly due to technical issues. In the area of Gulf of Corinth, we have also started a detailed seismicity mapping with the installation of the ARIS early warning system with 30 seismic stations. These data are valuable for the interpretation of the radon anomalies. And the conclusions are: first, a strong correlation between air temperature and pressure with soil radon concentration was found. Second, the Loutraki station installed in a geothermal area seems to be insensitive to atmospheric factors. Third, a clear anomaly was detected in the radon data before a magnitude 4.9 strong event in the Gulf of Corinth that resembles stress change. And four, the drop of the radon level was followed by a significant increase in seismicity, which lasts to this day in the area. Thank you.
Hello, this is Sun Nghiêm. I'm one of the chair of this session. So we are going into the question, answer, and panel discussion. So before that, I have some few words. First of all, I would like to represent my co-convener and my co-chair, Dr. Sun-hee Kim and Dr. Sanjay Shah, to thank, first of all, the speakers who present very interesting talk in this union session. Secondly, I also would like to thank the audience who participate in this session. There were as much as 77 people participating in this session. And I would like to thank the HEU personnel who participate and help us with this session. So then I have some comment for this session. First of all, the presentation in here actually presents some very interesting new concepts. As you can see in the several talks, these are not only interesting, but very useful. And one of the themes that I see raised up from many presentations in this session is the idea of proactive rather than reactive, because when the disaster already occurred, then it may be too late. So with that, I would like to have a senior to bring us up one, two, or even three most important questions. I did see that a number of questions already answered in the chat by the speaker, and if there are remaining unanswered questions, Sanjay would send those to the speaker to answer later. So with that, Sanjay would bring us up some question, and if we still have time, I would ask the speaker to give a quick take-home comment. All right, go ahead, Sanjay. I didn't see Sanjay. While waiting for Sanjay, I would like to point out that Lisa Moraska, because of the difficulty in the timing, she is not able to join in this panel discussion, but she is the first author of the letter that points out the importance of the coronavirus spreading through the aerosol. And this was signed by more than 200 scientists that brings to the WHO attention so that they recognize the importance of the aerosol pathway and actually modify their recommendation to cope with the COVID-19. So Sanjay, any most important question that you see that were not answered? Sanjay?
Hello, everyone.
Yeah, Sanjay actually copied all the questions and some of your answer in her file, and then she will send those out if there were any questions that were not answered. So Sanjay, do you see any important question at all that
I
were
think
not answered?
most questions are kind of focusing on specific presentations, like asking the tools available. I think we have a very broad audience from multiple types of institutions, including some from practitioners and companies, not just from the academia and the government, which is a very important factor in this case because there's a great need to involve multiple stakeholders in the decision making, as well as understanding the actual need from the first responders, as well as from the actual data producers. So far, I still think there are like a lot of questions about the broad topics that's relevant to this session. But feel free to pop up your questions in the chat box and just let or you just specify one speaker to answer them.
So with that, and while we are waiting to see any really critical or important question coming up, I would suggest that each of the speakers will give us a very succinct, less than 30 second take-home conclusion with regard to the fact that we are in the time that we have the compounding factor from various disasters that may occur at the same time, or it may recur again. So you can see the COVID as the first wave, second wave, and now the third wave. And on top of that, we have a really nasty wildfire and the flooding problem that may have an evacuation order on top of the COVID-19 and many other disaster may occur at the same time. So with that, I would like to go with the presentation order. So the first comment will be from Sagi Cohen. Go ahead, Sagi.
Can you hear me?
Yes.
Okay, so I guess I'm representing the flooding part of the disaster spectrum. What we see, there's a lot of exciting new things that happening right now with improving our ability to respond and predict floods. And from the remote sensing perspective, there's a growing capabilities and interest in understanding the actual impact. So going beyond the pure remote sensing or GIS analysis of extent or anything like that, or even depth, but how does it actually impact people and property and economy? So this is something that I see the community working towards.
All right, thank you, Sagi. The second presenter was Lydia Maraska, but as I mentioned earlier, she's not here, and I have already some comment on her presentation. So the next one will be William Lau. William, go ahead.
Yes, okay. So my main conclusion, my work, is that while everybody basically agree that the wildfire in Western US are due to global warming, but what we pointed out is there is a very strong missing link. How do you link the global warming itself, which is global scale, to the very local scale, which is wildfire? Okay, so we pointed out that there is a multi-scale interaction that involves a feedback loop between starting with global warming as the major driver and the change in the atmospheric circulation, which is associated with the change in the structure of the intertropical convergence zone, which is precipitation over the ocean, driving increased subsidence, and that sustained the drying trend for many decades. So you almost need a perfect storm like what we have in 2020 to get both the global, the regional, and the local, which is the wildfire, the pyrocumulus, all going to produce this 2020 spectacular event. So that's the main point. So we need now, I think this is even more confirmation that this is global warming, regional feedback, and local feedback acting together. Yeah, that's the main
Thank
point.
you, William. Yes, that was great. And then the next to give the comment is Bill Fry. Please keep it to 30 seconds.
Yeah, sure will do. I'm just going to echo the comments that Segi made earlier. We're very good as hazard scientists in understanding the physical processes of the Earth, I think, but we tend to have a lot of work left to do to understand the impacts to society and people. So a lot of the work that we need to see in the tsunami community going forward is mapping through hazard to probabilistic impacts, probabilistic risk, and loss for a given estimate or a given event to estimate what the damage is actually going to mean and make the right decisions based on that.
All right, thank you, Bill. The next one is Mark Svoboda. Please give your comment, Mark. Go ahead.
Thank you, Son. Can you hear me okay?
Yes.
Yeah, so I think if I had to wrap it up in 30 seconds, I would say of all the hazards, drought is perhaps the most analogous to climate change. We're talking about time steps from days to decades. We're talking spatial footprints from 1 kilometer to thousands of kilometers. So I think we have to think of drought in a new way and approach every year as if it will be a drought year in order to be proactive instead of reactive until such day that we have a perfect forecast. So thank you very much.
Thank you, Mark. And sorry, actually, Menace, can you give your remark?
So actually, I would also second what was just said, that we need to have proactive information in advance because so many different hazards are converging. For example, population distribution data can serve as the centerpiece in building a cross-sectoral strategy that can connect different stakeholders and participants in disaster response in the case that I presented, having fires, wildfires, and COVID-19. I will put some general remarks in the chat box so the audience can see some of the points I'm making.
All right. Thank you, Menace. And finally, Vasilio, can you give your final comment?
Yes, I think that with radon, there are very important prospects to assist earthquake forecasting. We're in a good way. We expect very good results in the near future. I think it is a very big effort from many scientists in the world. So we expect something good in the direct future.
All right, thank you, Vasilio. And finally, I would give everyone a final virtual round of applause. Thank you. All right, bye for now. Okay. I hope we see all of you in the real life sooner rather than later. Thanks again.
Thank you.
Thank you, Sam.
Goodbye.
Thank you.